Folks, this is lecture 5 of our introductory mechanical vibrations course. So on the agenda today, I have several items here. Most of it deals with some more modeling of single degree of freedom systems uh, when a complex situation is presented to us. And then towards the end, I will also talk about the energy method, which is an alternative way of getting equations of vibration, or the mother of all equations, but is applicable to certain problems that getting it from the basic principles of Newton's second law or Euler's method may be more difficult. Okay, so we'll talk about that towards the end. Now, let's start with a problem where a pendulum attached, which has a rod in a perfectly rigid rod, and attached to it is a point mass mg, and on the top there is a spring acting. So when you think about this is a single degree of freedom system, because if you take the mass and move it to the right, by just simply moving it to the right or giving that rod a certain specific rotation, the entire configuration is determined. So this is actually a single degree of freedom system. The question is, how does the mother of all equation look like? In other words, something times variable of interest double dot plus something else variable interest equal to 0. In other words, an effective mass times acceleration would be linear, or it can be angular depending on what you chose as coordinate, plus stiffness, whatever that stiffness is. Definitely it's not only that K. There may be, or in general there may be other things popping up. It's not may not be clear to you, but definitely gravity is going to pop up times the coordinate, whatever it happens to be. So the free body diagram of this bar, when it's tilted with an angle theta, so it looks like we are using the angle theta as the coordinate, and that is true. I could have used for example, the horizontal displacement of the mass, but that's not what I'm doing. I'm taking this angle theta as the coordinate, and the free body diagram is drawn here. There's a spring force, which is well, there is a spring force, which is actually K times the amount of stretching. Okay, K times the amount of stretching. But the amount of stretching, if you think about it, is going to be, assuming that we are using linearized theory, is going to be this length A times theta. If you look at this right triangle, the amount of deviation, which means the amount of stretching of the spring, is simply that A times the sine of theta. But if I assume sine of theta is approximately theta, in other words, theta is small, then the stretching of the spring is simply going to be A times theta. And therefore, times the stiffness is going to give you the force of spring. There is unknown reaction force up there, and then there's gravity pointing down. So what we're going to do, we're going to use the Newton's second law. Actually, when you take moment, it's not called Newton's second law, it's Euler's law, but that's okay. We refer to it Newton's second law. Sum of all the moment about a point O, a fixed point, equal to mass moment of inertia about that fixed point times angular acceleration. Remember, this formula is valid for two-dimensional analysis, and that point O can be a fixed point, reference point, or, for example, it can be CG. That also works. CG is not fixed, but it also works for that. But we are taking a moment about a fixed point. Now, what are the moments? There is this force, spring force, that has a moment arm, which is A cosine of theta, projection of this length A on the vertical axis, so it's right here. And because I'm taking counterclockwise as positive, this causes a clockwise moment, and therefore there's a negative sign here. there is mg times the moment arm, and the moment arm is that length, right? And that length is L times sine of theta, equal to the mass moment of inertia about the point O. Because you're assuming that the rod has no mass, it's only this point mass that has a moment of inertia about the point O, and that is the value of the mass times the length squared. This is from elementary physics or first dynamics class. And then theta double dot. Okay, so this is the mother of all equations, except that notice that these are uh, these terms are nonlinear, right? So what we're going to do for theta small, this is approximately 1, and sine of theta is approximately theta. I have already used this kind of a thing when I found what the stretching of the spring is, but we're doing it again. So here is the linearized equation, and notice that you can clean things up. You can clean things up, and you're going to get this expression, that term that's multiplied by the second derivative of the coordinate, which happens to be theta, by the way, is called effective mass. And this term that's multiplied by the coordinate itself, namely theta, is called effective stiffness. Remember, when we talked about these things last 2 weeks, we most of the time wrote it as mx double dot plus kx equal to 0. But that's only that thing applies only after you think about a single spring and a single mass. When you have a complicated situation, effective mass and effective stiffness can be calculated, and we did it. And therefore, the natural frequency is root of k, this number. This is the effective k, not k, effective k divided by the effective mass. So we have a more or less the same pendulum, except that it's inverted. And you will see that there is a fundamental difference between this problem and the one that we just did. Okay. Now, as far as the free body diagram is concerned, it's the same free body diagram. I'm choosing the same coordinate as theta right there. And sum of all the moment about the point O, about the pivot point in the counterclockwise direction, is positive. So when you look at this spring force, it has a positive moment, and the moment arm is just A times cosine of theta right there. This is the cosine of theta. This is the moment arm for the spring force. Mg is, of course, is going to be negative, a negative moment, and moment arm is going to be L times this sine of this angle, which is sine of theta. Now, for small oscillations, cosine of theta is approximately 1, sine of theta is approximately theta, and you rewrite that equation. Incidentally, that is the same moment of the mass about the point O, you know that, and you clean it up, and notice something strange happens. This used to be positive, now it's negative, okay? And of course, the natural frequency is calculated the same way, but there is the fundamental difference that I was talking about. In other words, for certain combination, of K, A, M, G, and L, the quantity under the radical actually becomes negative. And that means that there's something wrong. In fact, that pendulum, when it's inverted, like you usually get on the right-hand side on the top, is an unstable configuration. You can see that. Just think about it for a second. Suppose K was extremely small. This pendulum can wobble to the right or wobble to the right. It's by the smallest change, and it will not go back to the initial position of vertical configuration. So for certain combination, and I gave you an example where K is very soft, this is an unstable configuration, whereas the other one, irrespective of what that combination is, it is a stable combination and it's going to oscillate all the time. All right? That's exactly what I said. slightly modify this pendulum so that there is a damper present. Of course, I also changed the location of the spring too, but the damper is here and the spring is there. Okay. So these are the different distances that are given. And let's move on and find the uh, stuff related to this model. What we want to do is to get the mother of all equation for the system first. And then once we have it, we can find natural frequencies, etc., etc. So for coordinate, I'm using the same orientation for theta. And we're taking sum of all the moment about the point O, which is the pivot point up here, as equal to the F, basically mass moment of polar mass moment of inertia about that point O times the acceleration, angular acceleration. Now notice that this is a point mass, and therefore we are ignoring all these the mass of this rod, etc. And the J about O is mass of it times the distance from the point M to the point O squared. So this is from basic physics. Now we're going to draw the free body diagram. There is the pivot point is at O. There is a reaction force here. There is a damping force, which is proportional to the velocity. The velocity of this junction point is L2. L2 is this length times theta dot. So this is from, we are already assuming that linearizing the problem because we are assuming that the stretching is only of the damper is only along the axis, okay? Does not. So this is the damping force, and there is a spring force, which is just the amount of stretching. L1 times the angle theta that it makes is going to give you the amount of stretching, and multiply by stiffness. And there is the weight that's down here, okay? So first of all, we write ml squared theta double dot. That's the right-hand side, and then we look at these things. For example, the spring. Look at the spring up here, about the point O, based on the direction that I've taken as positive is negative. And the same thing with this damping force about the point O, based on the positive direction that I've assumed here. This is going clockwise. You can see that. And the same thing with the force due to the moment due to the, excuse me, due to the weight. Goodbye. Okay, I'm sorry, this allergy is killing me. All right, so this is the equation that we got. We take the moment about the point O, and we do a cleanup here for small angle. Cosine of theta is approximately 1, and sine of theta is approximately theta. So we just put all of the stuff in that expression and do a cleanup. So things multiplied by theta double dot, things multiplied by theta dot, and things multiplied by theta. So what you see here is the effective mass, effective damping or damper, constant, and this is the effective stiffness. The natural frequency is always square root of K effective over K M effective. So this is written here. And there is this is repeated. The equation is then up there, and there it's repeated. Now remember, we have damping, so the damped natural frequency is going to be natural frequency, undamped natural frequency omega n times square root of 1 minus zeta squared. Now here is the expression for zeta. Zeta, go back to 2 lectures ago, it was the ratio, it's called damping ratio, is the ratio of C over C critical, or C over C critical. There are different ways of writing it. For example, 2 square root of K effective, M effective, or C over 2m effective omega n. Okay, there are different ways of doing it. Now, if you plug this thing in, if the value of if this is zeta and plug this thing in, you get that. Really, I don't suggest that we memorize this formula. It's just that you know that and you know what that damping ratio is, and if you need it, you just stick it in there. But anyway, there we are. So what we have here is undamped natural frequency, damping ratio, and if you do a cleanup here, you're going to get damped natural frequency as shown there. So notice that this was a complicated problem, but we effectively reduce it. We reduced it to a single degree of freedom system because we know everything about single degree of freedom systems. Okay, linearized single degree of freedom system. We know the parameters. These are the parameters, omega n and zeta, and we know the response. When we go back, we found the solution to that equation. We found an explicit term which involves exponential, decaying exponential. There was sine, there was phase angle, there was an amplitude, etc. So we know everything. All right. Now I want to talk a little bit about these stiffnesses. Sometimes it's possible, it's very easy to find effective stiffnesses, and sometimes it's not. Okay. So, for example, if you have a configuration like that, back in mechanics, elementary mechanics, we call this thing as a series, two springs in series, and you can think about this whole thing as a single spring going from A to C, or an effective stiffness, which is 1 over K1 plus 1 over K2. Okay? So this is the way you get the stiffness, effective stiffness of two springs in series. These two springs are in parallel. So the effective stiffness is just sum of it. The both of these will actually resist the motion, okay? In parallel, actually. So K1 plus K2 springs in parallel. So for example, if you have a configuration like that, if you have a mass, for example, and you want to find out what's the natural frequency of vibration up and down of this, you notice that these two are in series. So its effective stiffness is 1 over, thing that I did up here. These two are in parallel, so you just add them up. Now these two are in parallel, you just add them up. And finally, this spring on the top and the spring at the bottom, they are also in parallel. It's misleading because you might say, wait a minute, it looks like that, but they're both resisting the motion. In other words, I could have taken the spring and put it up there. Okay, so yes, they are parallel, and oops, and there we are. So these two are in parallel, that's why you add them up. K1 plus K2 plus K5 plus this guy right there. Okay. Now things don't always look like that. You might have a configuration as shown here. Now obviously these two springs both resist the motion of that in parallel. And also there's a third resistance, which is coming from the beam. And remember that we talked about this thing last week. This beam effectively is a fancy spring with a stiffness which has material properties in it, cross-sectional moment of inertia, and the length cube. So this spring, there are three springs in parallel with each other. And there we are. K1 plus K2 plus that fellow. Okay, for the beam. So I'm sorry, when I say K1 plus K2, because the K over 2 or K over 2, they add up to K, okay? These two added up is going to give you a K because they are in parallel, K over 2, K over 2. And this is also in parallel with these, so it's just going to add up and you get this. All three springs are in parallel. All right, here's another situation. Now, when you look at this, you may not see any spring, but really there is one. There is one due to the beam that we just discussed a minute ago. Remember, it was right there, EI, 3EI over L cube. This is for the beam, 3EI over L cube. So there's one for the beam, 3EI over L cube. And this rope actually also acts as a spring. Okay, it's a stretches, like that's what a spring is. So we know from, I mean, if you know it, if you know the cross section and you know the length and things like that, we did this thing last week also. And AE over L, if you think about the rod, I mean, string is pretty much similar to acting, or a rope acts similar to a rod under extension AE over L. We did these things last week. So these two springs both resist, but they are in series. Okay, when you think about this thing, they are in series. Just think about it. This spring and that spring, they're not parallel, they're in series. So the equivalent value is 1 over KB plus 1 over KR. Okay, so yeah, and if you look at K equivalent is 1 over that whole shebang. Okay, but anyway, when the springs act in series, they behave like so. And yeah, that's pretty much it. Now, here's another example where you have a weight hanging to this effectively. Remember, this weight can oscillate up and down, right? Its mass can also. And what is resisting that? There's this bar with the stiffness, if you want, AE over L, if no bending was involved. But if there's bending involved, it's more complicated. The point is that there is a stiffness due to the AC, and there is a stiffness due to this cable. Okay, and these two springs, these two springs, okay, they're not in parallel because one of them is, they're both actually slanted. Okay, so the point is that they can be combined together and should be combined to get together if you're interested in the vibration up and down. But what the value of K equivalent is not obvious. And we're going to need some more sophisticated technique, such as energy expression that we're going to discuss in a few minutes. Okay, so don't just add them up. Once you know the configuration, you can find K1 and K2, but don't just add them up and claim that I can solve the problem of the vibration of this mass based on the sum of these two. That is not the case. Okay, now we're going to do energy methods. Okay, so let me remind you what the idea is. In the absence of any dissipation, in the absence of any energy loss, of course, energy is conserved. We're interested primarily in mechanical energy here, but yeah, so we're not interested in thermal energies and things like that. But anyway, so this you all remember from your elementary, physics class and mechanics class. For example, in the ideal situation when there's no energy loss, such as no friction or external forces applying to the system, which pumps in energy into the system, no external forces, no friction, no energy losses, otherwise energy is conserved. And mechanical energy is what you're interested in. So the idea revolved about there are two kinds of energy. There is a kinetic energy in when things are in motion, and there is potential energy. So T is usually represented by or represents kinetic energy, and that's the way it is in our textbook. And this is potential energy. The sum of it is constant. If the sum of it is constant, then the derivative of that expression is zero. Okay? So this leads to the mother of all equation. Because the total kinetic plus potential energy is constant in the ideal situation, you will see that we can get the equation of motion, the mother of all equation, based on the fact that the derivative of this as a function of time is zero. Okay? Now, you might say, well, what happens if there are energy losses? Well, you can't go that route anymore. There is a parallel pathway which is based on variational methods, Lagrangian and things like that, that we don't do in this course, okay? We don't treat that module, the energy, conservation of energy we do, okay, for ideal situation. But when there is damping present, non-conservative forces present, then we are not dealing it in terms of energy stuff in this course, okay? All right. Let's recall a few things from our statics class. Suppose we have a spring attached from the ceiling, just to make it look easier to understand, and we attach a mass to it. This is the unstretched length. And of course, what happens is that because you attach the mass to it, slowly this thing stretches, and this is what we call static deflection. So our coordinates in this course are primarily measured from the equilibrium position. So when I say x, for example, it's going to be x displacement from this line, not from the line up there, not from x somewhere else. Okay? Most of the time it's going to be like that. Now, what is the free body diagram on this mass? There is a stretching of the spring which causes a opposing force, k times delta, and there is the weight. Okay? Now, and this is pretty much what I said a couple of minutes ago, is that the displacement that you measure is from this dotted line. So it's beyond uh, unstretched plus static deflection. Okay, so the amount of stretching of this spring in that configuration, in this configuration, the amount of stretching of the spring is x of t. All right. So when you look at an arbitrary location, suppose that the mass is at this location. Well, there is it has moved from that equilibrium position. See, from this equilibrium position, it has moved. This was the equilibrium position. We measured distance from there. So it had moved down. So it has lost energy, potential energy. Remember MGH? Do you remember that? MGH, but this is going below our datum line. So there's a minus MGH. It has lost that much energy due to potential uh, gravitational potential. But it also, the spring has also stretched. Now, how much has it stretched? Well, there was an initial stretching of delta right there because of static deflection, and now it has stretched by another amount x of t. So the total stretching in that spring is x plus delta. Delta was the static one right there, and x on top of that. So the amount of stretching in the spring is x plus delta. Now, you remember from your, again, mechanics class, if you take a spring and you stretch it by some amount, the amount of potential energy stored in that configuration is 1/2 of the stiffness times the amount of stretching squared. And there is the amount of stretching coming from two sources. Okay? I'm going to do this uh, development of this section in two different ways, parallel ways. First one is looking at the total potential energy and calculating it at the equilibrium position, okay, at this position, and then calculating it at the stretched by x position, and say that because energy is constant, the sum of the two must be, or the two expressions at the equilibrium position and at the stretch position must be the same. So this is one way of doing it, and that's what this derivation will show you. Total potential energy is consisting of two parts, as you can see, and we already mentioned that. One is due to the total stretching of the spring, okay, and then potential energy due to the gravity, but this position, because it went down below that, it's a negative sign. So there is the expression for potential energy at an arbitrary position. So we're going to look at, and obviously the kinetic energy at the equilibrium position, it was, that was the equilibrium. There was no velocity. So the potential, the kinetic energy is one half velocity squared, and there we go. So we're going to equate these at two different locations. One of them is at the equilibrium position, and the other one is at the stretch position. So here we are. At the equilibrium position, there is no kinetic energy. T is zero, and potential energy is only the one that's stored due to that static deflection, one half of k delta squared. Now, the potential energy at an arbitrary location, let me go back. It was right here. This is at an arbitrary position. See, this is the potential energy at an arbitrary position after pulling it by x of t, and this is the kinetic energy of it right there. So let's go here. That's what I did. Potential energy at an arbitrary position plus kinetic energy at an arbitrary position equal to potential energy at the equilibrium position and kinetic energy at the equilibrium position, and it's not moving, and therefore it was zero. If you clean this up, you'll notice that first of all, there is if you expand this thing, you get 2x delta. One half is here plus x delta and a minus x delta, so those will cancel. This term on the right-hand side will cancel the first term over here, one half of k delta squared. It cancels that. And after a cleanup, you get this. So this comes from the fact that we're saying that total energy at the equilibrium position equal to total energy at an arbitrary position. And now we can differentiate this thing. If you differentiate that, you get a 2k x dot, and you differentiate this, you get 2x dot x double dot. This is from elementary calculus. And divide through by x dot, you're going to get the mother of all equations. Now, I'm going to do this thing a different way in a minute. I don't particularly like this way of explaining thing. At this location, here's the total energy. That location, here's the total energy. Equate them, clean it up, and then differentiate it. I don't particularly very fond of that. Now, by the way, notice that G disappeared. G disappeared from the mother of our equation. So another way of looking at this thing is saying, okay, let's measure things from the equilibrium position. Stretching is x from the equilibrium position. We don't care what happened before that. So the energy stored in the spring is 1 half kx squared. And it's moving at velocity x dot. So the kinetic energy is 1 half mass times velocity squared this. This sum is constant. And its derivative is 0. So let us just go ahead and write the sum. Differentiate with time, set it equal to 0, and we get this equation, divide through by x dot, and there we are, the mother of all equations. So that's why I said another way of looking at the same problem. Okay, we got it not based on Newton's equation of motion. We didn't get it by saying sum of all the forces equal to mass times acceleration. We got it by the statement that the energy is conserved, and therefore there we are. Energy is constant, total energy is constant, derivative is 0 because it's constant. And then once we got that, we just just cleaned it up, divide through by x dot. So we're going to do a bunch of problems. Okay. Example that we did last week, and we derived it based on equation of motion, Newton's second law, and also Euler's law. And we would like to repeat that problem based on energy principles. There's only one difference between my drawing that was done last week and this one. There, I drew the angle theta to be positive, the coordinate theta or angle theta to be positive in the counterclockwise direction. But here I'm drawing it to be positive in this direction. So remember, this is entirely up to you. The only difference is that if I draw it like that, I get the standard formula x equal to r theta and x dot equal to r theta dot, etc. If you go back to the last week's lecture, theta going counterclockwise direction, there's going to be a minus sign here. So this is fine. Uh, it's not going to change the answer. It's just that there's a difference between what the drawing was back then and what the drawing is now. Now, these should be obvious, and if it's not obvious, please go ahead and review the last lecture that we did last week, another lecture number 4, and these are obtained for you based on basic principles of kinematics. Now, assuming that everything is measured from the equilibrium position, and by the way, this cylinder or cylinder is rolling without slipping. Okay, so it's rolling. Now the kinetic energy is, first of all, this mass has a velocity that's moving in translation. So it's going to be 1/2 mass velocity squared, but the velocity of this mass center is x dot. And then this is also rotating, for example, about the mass center. You can see that. So we know from the stuff that we have done is in mechanics, dynamics, 1/2 of, because it's a rotational motion, it is not m, it is polar mass moment of inertia about the point O being the center, for example, CG, and then theta dot squared. 1/2 j omega squared. Omega is theta. Now, based on this constraint equation that we have here between x and r are related, x and theta are related, either there or there, we can write everything in terms of x instead of theta. Remember, this is a single degree of freedom system, and there is a constraint which relate the coordinates x and theta, and this is what I've done. Now, as far as the spring goes, it just stretches by the amount x, so the energy stored in it, potential energy stored in it, is 1/2 kx squared. So the sum of these two is going to be constant because there are no friction, there are no losses. Well, I really shouldn't say that there's no friction. There is friction because the thing is rolling, because the ball is rolling. Okay. However, we are assuming there are no losses. Notice that there is friction here, but that friction happens to be taking place at the contact point, and the contact point on the ground is not moving. So that friction does no work. There is friction here, but there is no loss because that work does not actually, that friction force does not do any work. So be careful, because otherwise you might say if there's friction, there must be losses. Well, you have to be careful. No losses here. So you write down all of these things, write down the expression for T and U right there. Okay, this was the T, kinetic energy, translation, rotation, and this is the spring energy, differentiated based on elementary calculus. So for example, derivative of x dot squared is 2x dot x double dot. Again here, derivative of, just write it down, okay, because use the chain rule here, 2 in the front, that thing to the power 2 minus 1 right in here, and the derivative of what's in it with respect to time is going to be x double dot divided by r. And this, of course, is going to be 1/2 times, there is 2 missing here. That's a typo here. There's a typo here, please. This is going to be 2x x dot. Okay, so there is a typo 2 missing here. And if you clean this up, divide through by, if you divide through by x by x dot, you're going to get the k. K is going to be remain a k, okay? But then here, effective stiffness is k. You wrote it down, and effective mass is just the sum of these two. Okay, sum of these two means clean up whatever is multiplied by x double dot. You're going to get your answer. Okay. Now, if you assume that this is a disk, the mass moment of inertia about the center is 1/2. Polar moment of inertia is 1/2 mr squared. Okay. Now let's go ahead and look at the same type of problem, except that it's a pendulum. So this is the classical simple pendulum problem, massless rod. So we want to get the equation of motion based on energy principle. So first of all, the equilibrium position is taken as this datum. Okay, so the uh, potential energy due to gravity loss or gain of it is measured from this datum. There's no spring here, but the gravity will play the role of that restoring force, the role of that spring. First of all, as far as the kinetic energy is concerned, it's 1/2 of mass times velocity squared. Now, velocity, if I use theta as the angle, as the coordinate here, then the velocity of this point is going to be L times theta dot. This is from basic dynamics. Okay. And the potential energy loss is only due to gravity. And of course, if it goes up, it gains potential. If it goes below the datum, it loses potential. So this height, which is L times 1 minus cosine of theta, remember this whole thing is L. This projection is L cosine of theta. You subtract, you get this height. It's written there. And you write the sum of that equal to 0. Again, we are assuming there are no energy losses, etc. So we're going to get, there we are. Okay. When I say energy loss here, for example, no air resistance and things like that. Right. There is, even though there may be some energy friction because of the joints and things like that, but this point is not moving, so that's all right. Just clean it up, differentiate it, clean it up, differentiate with respect to theta. So if you differentiate theta dot squared with respect to theta, you're going to get theta dot, theta double dot. Two of them. Okay, there's two of them. Okay. And then different derivative of cosine is negative sine, so that minus sign goes away. And if we assume that angle theta is small, so we have goes away. We're going to have L theta double dot here plus G theta. Okay, this is dividing through by theta dot, and here is the mother of all equations, and therefore the natural frequency is square root of G over L. Okay, let's move on. This problem was done for you again last week, but we got it based on, again, Euler equation, in other words, balancing or summing up all the moments about the pivot point here and equating it to mass moment of inertia times angular acceleration. We're going to repeat that using the energy method. Okay. So let us assume that theta is measured, just like we did last week. Assume that this horizontal position is the equilibrium position. Okay. First of all, the thing that has kinetic energy is this rod that is turning and about the point O. So we know that the kinetic energy of it is 1/2 of mass moment of inertia about the point O, and times angular velocity squared. Okay, we know that this is from dynamics. And then as far as the potential energy is concerned, these springs, they both, one of them compresses, the other one stretches, but the amount of stretching in it does not uh, matter whether it's compression or tension. The potential energy in it is 1/2 kx squared. Now, x1 and x2 are related to theta. This is a single degree of freedom system, so we know that based on the geometry, x2, for example, is b theta, and x1 is a theta. Okay, so we know that. And just replace everything in terms of theta, because that's going to be our variable. And this is what you're going to get. Here's the expression for potential energy. And the sum of kinetic plus potential energy equal to 0. You're assuming the ideal situation, no energy losses. Just write it down and literally, patiently just divide it or differentiate this thing. Differentiate it. When you differentiate theta dot squared, remember you get theta dot, you get 2 theta dot theta double dot, but the 2 kills this 2, etc. Here's the mother of all equation, but divided by theta dot, of course. There's the mother of all equation. Here's the natural frequency, the same thing that I got before last week. And what we like to do next is to show you what is the effect of the mass of a spring. So far, we assume that our springs are all massless, and therefore uh, we didn't take it into consideration. And I cautioned you that this is an approximation. The mass of the spring can be important, but the only or one way of bringing that into the picture is through the energy method. So here's the situation. Suppose this spring has a mass of ms. Okay, the mass of this object is here, but the mass of the spring is mx. So the whole length of it is having a mass ms. So if I go to some distance away from the support, location y, and a little bit past that, in other words, if the length of this piece of spring, the short piece of spring dy, is dy, we can find the mass of that little piece. See that? Y and dy, this piece of spring, which is of length dy, will have a mass, which is proportional to its length. There we are. So dy has a mass of dy over L, because the whole spring has length L, and times ms. Okay, now, this notice that this little piece of the spring, which has that mass, also have velocity, and the velocity of it is actually proportional to how far away from the support you are. For example, if you're way down here, then the velocity of that point of the spring is the same as velocity of the mass. So when y is equal to L, you get the velocity of the spring equal to x dot. When you're way up there, it's not going anywhere, so y is 0. So anyway, that little piece of the spring has a velocity which is like so, in terms of the velocity of the mass that's hanging down here. Now, the energy of the spring is kinetic energy of these little pieces. So you take one, you have 1/2, okay, you take 1/2, okay, the mass of this little piece that we already worked out here, times the velocity squared. Here's the velocity squared, velocity of that little piece squared, and just clean it up. Just clean it up. What do I mean by clean it up? Ms is constant, it comes out. L is constant, it comes out, and you get the integral of y squared dy. Okay? Integral of y squared dy from 0 to L. You know, integral of y squared dy is y cubed over 3. So if you do this bit of algebra here, you get the kinetic energy of the spring is this. So later on, this is the extra mass that has to be accounted for, okay? Later on, we're going to add this thing to the kinetic energy of the block. There we are. And they both have x dot squared, so I factored it out. And the natural frequency, if effective mass, you can see that the effective mass is the mass of the block plus a third of the mass of the spring. So this is how the natural frequency of the single degree of freedom system has to be modified if we are to account for the mass of the spring. Now, based on what I just told you, if you have axial vibration, for example, of this setup, whatever the mass of this rod is, that is your spring. That's acting as your spring. You take a third of it. If you're dealing with bending, whatever the mass of the spring is, take a third of it, just like that. Done. And so basically effective mass becomes the mass of the block plus whatever the mass of the spring is. Okay. For this configuration, this is the mass of the spring. For that bending configuration, again, m over 3 is. So, yeah. If you're dealing with torsion, there is a modification to be made because we have to take I about the axis. See, I about the axis of that vertical line, vertical spring. So we know what I of the shaft is. See that I of the shaft? This is going to last week. I of the shaft is going to be, think about it as the mass of the shaft, but because we use I, because it's rotational motion, is 1/2 of the mass of the shaft times R of the shaft squared. And you cap for if you're to account for this mass because it's acting as the spring, take a third of this. This we know. You give me the dimension, I know what this thing is. And take a third of it and include it in the mass of the system when you're doing natural frequency calculation. This is mass of the system, the J of this fellow plus I of the spring that is basically I bar over 3. Okay. And we just go ahead and do the problem. Now, we also want to see how the restoring mass. Remember here we don't have a spring here. Okay, we want to find the natural frequency, but we also want to get this. We want to get this based on energy method. Okay, this has nothing to do with the mass of the spring taking a third of it, etc. It's not that. It's just that we want to get this equation, the natural frequency of vibrations of this system that we did last week based on energy consideration. Please don't mix up. I'm done with the subject of the previous two slides, which was how to account for mass of a spring. We don't have a spring here, okay? So this is just to get the manometer equation, vibration of the manometer liquid, in terms of energy balance. Okay, the restoring force again is gravity. That's fine. So what we have to do is notice that at any time t, there's two columns of water which are have gained potential energy because of the motion. There is this column, which is area times x is going to give you the volume of that, multiplied by gamma is going to give you your basically your mgh. Okay, so this is the volume, this is the volume, this is times gamma is going to give you mg. This is your weight, and it's going to go up by we can approximate it by x over 2, because remember, this piece, although the surface goes up, the mass center of it is halfway between. That's why it has an x over 2. It's the same thing for the other one, same thing for the other one, and you just clean it up. You're going to get gamma ax squared. Okay. Kinetic energy is basically the mass of the liquid, the entire liquid, which is translating with a velocity x dot. So 1/2 the mass of the entire column of liquid, right? That the entire thing. the entire thing, the entire U-shaped thing, uh, times velocity squared. Okay, and just write it down, clean it up, put these things in, differentiate it. Remember, you have x dot squared, you get 2x dot x double dot, divide through by x dot, and you get your mother of all equation, and you can find your natural frequency of oscillation. Here's the more scary problem that we're going to do in just a minute. Okay, this is a more scary situation as far as the problem is concerned. It's coming out of Inman's book, and uh, it's related to the nose wheel of the landing gear of an aircraft. Okay, so the steering mechanism for the nose wheel. Now, there's a couple of things you should realize is that this is single degree of freedom system. When the disk moves, this moves with it. These are assumed to be geared, which are meshed together. So notice that this theta is drawn like that, but the x is drawn like so. But notice that if theta goes in this direction, actually it makes this block move to the left. The moral of the story is that there's a minus sign. They're related, but there's a minus sign here. If I had drawn theta going in the other direction, then there will not be a minus sign here. Or if I had drawn x to be in the other direction, there will not be uh, a negative sign. So just be careful, although it doesn't, when you use energy method, this particular negative sign is not going to hurt us, or it's not going to help us, but just be careful with how you draw your coordinates and how your constraints equation are. Okay, so yeah, so let's move on. Notice that when these are engaged, there's two kinds of energies that are gonna, kinetic energies that are gonna come into the picture. One is because rotation of this disk. The other one is because of translation of this bottom block. Okay, so the kinetic energy of the bottom block is 1/2 mx dot squared. It's a translation. And kinetic energy of the disk, because it's rotating, is 1/2 j, polar moment of inertia, about the center, times angular velocity squared. Okay, so this is the expression for kinetic energy of the system. Now, it is true that based on these we can write everything in terms of x. So you find x dot based on that equation. And notice that you find theta dot based on this equation. And notice that because you're squaring things, even if these signs were wrong, it will not affect this part of the calculation. Now, when it comes to potential energy, this K2 stores energy because it's being compressed or stretched, depending how things go. And this shaft here also stores energy. It's a torsional spring. Now, remember, we got the expression for the stiffness of a shaft under torsion. You can go back, see what it is. It involves shear modulus. It involved, polar moment of inertia of the shaft, etc. But anyway, so that's beside the point, because you can go and find out what was it that we had there. But it's denoted as K1. Okay, so 1/2 K1 angular displacement squared, 1/2 K2 translational displacement squared. Okay, so if you write everything in terms of x, so from this equation you can solve for theta, write everything in terms of x, you get that expression here. Now we know that the sum of these two is constant. Sum of these two is constant, so when you differentiate it, you get 0. So very patiently differentiate these terms. Derivative of x dot squared is 2x dot x double dot. derivative of x squared is 2x dot, and divide through by x dot, you're going to get the mother of all equation for this oscillatory motion, okay? In other words, if you move the block a little bit and let it go, this whole thing will go back and forth, assuming there's no damping. And the natural frequency of that oscillation comes from this. Here is your effective stiffness, and there is the effective mass. So you just plug it in and do a little bit of cleanup, you get this expression. Okay, so that's pretty much it. See you on Thursday.